Calculus, Chapter 3, Section 7, Higher Derivatives. I'm your host, Dr. D. Okay, that's it. Let's get started here. So today's lesson, we're going to be talking about some things that have practical applications, but also we're going to be talking about some abstract concepts. And this is one of the things that makes calculus a challenging subject. You have to actually think abstractly. So sometimes that doesn't work out very well. Okay, let's give it a shot. Okay, so we know we've got an original function. So we'll call it either f of x or y, where y is a function of x. So that's our original function, and that's going to be the behavior of f, or the behavior of y, with respect to x. Now when I say with respect to x, what I mean is x is the independent variable. It's the measurement of our function. So as x gets larger, what does f of x do? Does it get larger, or does it get smaller as x gets larger? So that's our original function. Now f prime of x, or dy dx, that's going to be the first derivative, which is the rate of change of f of x with respect to x, which means it's the slope of our original function, the rate of change of our original function. Now, f double prime of x, or d2y over dx2. Now, I don't know why they don't just make it dy2 over dx2, but they didn't, and you need to learn it this way, d2y over dx2. That's called the second derivative. Now, the second derivative is basically the derivative of the derivative. So that's the rate of change of f prime of x, or of d2y over dx2, or y double prime. The rate of change of the rate of change of the original function. Now let's think about what that means. This is what I was talking about at the very beginning, where we need to be able to think a little more abstractly. So let's say we've got a function where, here's our graph. Now, the function is, let's just say f is increasing with respect to x. So, yeah, you know what? I actually don't need this whole thing. Okay, so our function is increasing with respect to x. Well, that increases with respect to x. Or this, the function is increasing with respect to x. Or the function is increasing with respect to x. Now, increasing with respect to x basically means that as I go to the right, the function is increasing. As x gets larger, f of x gets larger. As x gets larger, f of x gets larger. It's going up as I go right. Now, this first function, it's supposed to be a straight line, that has a steady rate of change, or in other words, a consistent slope through the whole thing. Now, what's happening here? Well, it's increasing, but the slope is getting larger as I go. In other words, the first derivative is getting greater as x gets greater. So in other words, this is increasing at an increasing rate. So it's not only going up, but it's going up steeper and steeper and steeper. So it's increasing at an increasing rate. Now this is also increasing, but it's getting shallower and shallower and shallower. So it's increasing at a decreasing rate. So the first example is an example where the first derivative is a positive number. The second derivative equals 0. Why? Because the rate of change of the first derivative is 0. The first derivative is not changing at all. So this is a linear increase. Second derivative is 0. Now, this is an increase, but it's not linear. It's increasing at an increasing rate, which means the first derivative is positive. The second derivative is positive also, because it's going up faster and faster and faster. Now, this example, the first derivative is positive everywhere because it's a positive slope the whole way. But the second derivative is negative. How do I know? Because the first derivative is getting smaller and smaller and smaller. So that makes the second derivative negative. If the first derivative is decreasing, the second derivative is negative. Now, f triple prime, or d3y over dx3, is the third derivative, or the rate of change of the second derivative. And now, once we get past 3 primes, we don't want to go 4 primes, 5 primes, 16 primes, that'd just take way too much. So we just put a 4 in parentheses. So f4 of x, or the fourth derivative of f with respect to x, d4y over dx4. That's the fourth derivative, that's the rate of change of the third derivative. Okay, cruising onward. So let's say we have a function f of x equals x cosine x, and we want to find the second derivative. Okay, well, if we want second derivative, we need the first derivative first. So we take our first derivative, and this is a product. So we better use the product rule. Okay, so it's first times the derivative of the second. Derivative of cosine is negative sine, remember. And then we go plus second times the derivative of the first. Okay, so our first derivative then equals negative x sine x plus cosine x. All right, now we're ready for the second derivative. So we go f double prime of x equals. Same thing here. We have a product, so we better use the product rule. So we have first times derivative of the second plus second times the derivative of the first. Okay, now we take the derivative of cosine x, which is negative sine x. Okay, so now let's simplify this. So f double prime of x equals negative x cosine x minus sine x minus another sine x. So that's going to be minus 2 sine x. Bam! That's it. Game over. Okay, let's see. Yeah, that's basically what they have in the book. Okay, so it's time to cruise onward. Okay, now here is where these multiple derivatives have practical application. S of t is the displacement of some function, the displacement of some object as a function of time. Now, if I want the derivative of that, then I'm going to have the rate of change of s, which ends up being the velocity. V of t is the velocity as a function of time, the first derivative of displacement. Now, if I take the derivative of the velocity, then I have the acceleration, which is the second derivative of displacement, which is the rate of change of velocity, acceleration. Now, if I take the derivative of acceleration, that would be the second derivative of velocity, or the third derivative of displacement. That's the rate of change of A with respect to time. That's called jerk. That really is called jerk. It's not something I just made up here. Now, I remember when my brothers and I were kids, there was a vine swing that swung out over a ravine. And so we would pull this vine up to the precipice of the ravine, and then we would swing out over the ravine on this vine that was hanging from a tree. It was probably about a 15-foot drop from where we swung out over the ravine. Now, my brother swung out, and somehow the vine adjusted as he was swinging, and so he fell off, and he broke his arm. So he came home, and he was telling my parents about it. His analysis of the situation was that it was the jerk that did it. And I had to agree. Got to think about that for a second. Okay, so jerk actually is a rate of change of acceleration. Okay, so we start with a function s of t equals t cubed minus 6t squared plus 9t, and we want to find the acceleration of this particle at any time t. That means any time we'll be able to find out the acceleration of it. Well, if I want the acceleration, first I have to get the velocity. So velocity is going to be the derivative of displacement. So that's going to be 3t squared minus 12t plus 9. Now, acceleration is going to be the derivative of velocity. So we've got 6t minus 12. That's acceleration. Now, notice one thing here. Every time we take a derivative, we decrease the degree by 1. That is of a polynomial. So I have a third degree, take the derivative, I get a second degree, take the derivative again, I have a first degree. Now, if I take the derivative again, which they didn't ask us to do, but this will be like bonus coverage. So this is just going to be 6. So the jerk is going to be a constant 6. Now, if I took the derivative any further, every other derivative I would take would be 0. So once you get to a linear, then every derivative after that will equal 0. Okay, now, that's what they asked us is, find the acceleration at any time. Now, next, they ask us, what's the acceleration after 4 seconds? Well, all I do is plug in 4 here. 6 times 4 is 24, minus 12 is 12. So the acceleration, if the, notice displacement would be in feet. Velocity would be in feet per second. acceleration is the rate of change of feet per second. Well, that would be feet per second. Or, to shorten it, we say feet per second squared. But really, feet per second describes acceleration better. We know on Earth, our acceleration is 32.174 feet per second per second. What that means is, when I start to fall, I'm falling at, well, after the first second, I'm falling 32.174 feet per second. And every second after that I'm falling, my fall rate increases by 32.174 feet per second. So the first second, it's 32 feet per second. The second it's about 64 feet per second. The third second, it would be about 96 feet per second. So every second, I'm increasing my velocity by 32 feet per second. So that's 32 feet per second per second. That's acceleration. Now, in this case, we would have 12 feet per second squared would be the acceleration of this particle at 4 seconds. Okay. So, oh, and notice in the book, example 2, that's what we just did here, their acceleration is 12 meters per second squared. So their particle is in France. Ours, the good old USA, feet. Feet per second squared. Okay, now, next, let's graph this puppy. Okay then. Okay, so the red function is my original function. Y equals x cubed minus 6x squared plus 9x. It's a cubic, so it's got 2 terms in it. Now the blue is the derivative of the red. So let's just mark this right here. We've got blue is rats. Okay, let's just move this over here. So, okay, so red is f of x. Blue is f prime of x. And the green is f double prime of x. Okay, now, what I want you to notice here, the original function, f of x. Now, if I want the derivative of f of x, then what I want to do first is I look at the maximum right here. Now that's a point where the slope is 0. Well, that means my f prime of x should be right on the x-axis, and it is. If I just go straight down from there, then I've got the derivative of the red is the blue. The derivative of the slope being 0 means that my derivative is 0. Now, the other thing I do is I look at the minimum, and notice it also is a place at 0. Now notice the red goes from a positive slope to a negative slope. And that's what the blue is doing. It's going from above the x-axis to below the x-axis. Now here we've got a negative slope going to a positive slope. So the blue is going from below to above the x-axis. So that's the first thing that confirms for us that the blue is the derivative of the red. Now let's do one more thing. look at the point of inflection for the red. Okay, where is the red at maximum steepness? Well, first of all, if I go to the left, it just keeps getting steeper and steeper, so there is no maximum steepness. Well, and it's in a positive slope. Notice here, the f prime is going to go up forever. There is no maximum of f prime. It's just going to keep going up forever. Now, if I hit the zero slope, now I'm going back down. Well, it's getting steeper and steeper and steeper and steeper up till right about here. Now, right here, it begins to get less steep until here. Well, notice that's right at this point right here. So right here is what we call the point of inflection of the red function, or the point of maximum steepness. And that's a negative slope, so the most negative f prime ever gets is right here, and that's its minimum of f prime. Now, we can do the exact same thing with looking at f prime and trying to figure out f double prime. Well, f prime goes from negative slope to positive slope, and it changes right here. So we would expect f of x, or f double prime, I mean, to go from negative to positive right at this point, which it does. And notice another thing. There is no point of inflection of f prime of x. That means there is no maximum steepness. If I go left, it's getting steeper and steeper in the negative direction. And if I go right, it's getting steeper and steeper in the positive direction. So there is no maximum, there is no minimum of f prime, or f double prime, I mean. So that's it. Now, what you're going to be doing later on is you're going to be given 3 or 4 functions. 4 is even more fun. And what you have to do is decide which one is the original function, which one's the derivative of the original, which one's the second derivative of the original, which one's the third derivative of the original. And remember, first thing to think of is the original function will always be the one with the greatest degree. And then the degree goes down as you go. Secondly, you look for a max and a min, and for the max, you're looking for something that goes from negative, or from positive to negative. And for the min, you're looking for something that goes from negative to positive. And so that's how you're going to point those out. So the red is my displacement. So my particle, if you start at 0, 0, let's say there is no negative time. So if we start at 0, 0, the particle begins to go in the positive direction. At some point in time, it stops going positive and starts going negative. And then another point in time, it stops going negative and begins going positive again. And so the rate of change is going from positive to negative. So there's the velocity, blue, going from positive to negative. And then it's going, okay, so it's going up, 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 slower and slower, and when it gets to the top, it starts going back down. Now, if I toss something up in the air, that's what's going to happen. It's going up, but it's going slower and slower. That's what the blue curve says, is its velocity is going down, even though it's positive. See, if you have a positive velocity, that means the particle is still going up. But the moment the velocity changes to negative, now your particle is beginning to come back down. because it's going in the negative direction, negative velocity. Now, this is not, on Earth, we're not going to have a particle going a third-degree function because we don't have something that goes up, comes back down, and then goes back up again. That would be pretty cool if something did that. But this particle does that. So you notice the velocity goes from negative back to positive again. So that's, now acceleration is going from negative to positive, and then it never goes back down to negative again. Okay, cruising onward. All right, now, we've got f of x equals 1 over x, and we want to find the nth derivative of x, f of n of x. So let's find our first derivative first. So f prime of x equals, well, to make it simpler, let's just make this x to the negative 1. So now x prime, or f prime of x is going to be negative 1 x to the negative 2. Now, f double prime of x is going to be negative 2 times a negative 1, which is a positive 2, times x to the negative 3. And then f triple prime of x equals negative 6 x to the negative 4. And then f, well, the fourth derivative, of x, or fourth derivative of f with respect to x, is going to be negative 4 times negative 6, which is positive 24, x to the negative 5th. Now, this is going to be challenging to find a pattern, but that's what we're trying to do. It's almost like when we were looking at sequences and we're trying to find the pattern of the sequence. Well, let's do something here. So the original function is 1 x to the negative 1. Now, the derivative becomes negative 1 x to the negative 2. So what I can do is I can write, notice we've got, the first function is positive, the second, or let's say the derivative is negative, the second derivative back to positive again, then negative, then positive. Now if I take this derivative, it's going to end up being negative again. So clearly what's happening is I'm alternating signs. So what I can say is the nth derivative of x is going to equal negative 1. Now, is it negative 1 to the n or negative 1 to the n minus 1? Well, if I say negative 1 to the n, then the first derivative will be where n equals 1, and that makes it negative. The second derivative, n is 2, well, negative 1 to the second is positive. Negative 1 to the third, back to negative. Negative 1 to the fourth, back to positive again. So we know we have a negative 1 to the n times some other junk. But we know it definitely alternates signs, so we've got negative 1 to the n. Now, let's look at the numbers in front of our x's. So, first we have 1, and then we have 1 times 2. Because notice, we went the 2 times 1. Now next we have 2 times 3, or 1 times 2, 1 times 2 times 3, that's 6. Next we have 1 times 2 times 3 times the 4. That's 24. Now if I go again, 24 times 5, well, we don't have to know what that is. We know it's 1 times 2 times 3 times 4 times the 5. And notice we already took into consideration the change of sign. So the coefficients in front of all my x's are going to be, notice for the first derivative, it's 1 factorial. Second derivative, 2 factorial. Third derivative, 3 factorial. Fourth derivative, 4 factorial. And so on. So the nth derivative is going to be n factorial. Piece of cake. Okay, now one more thing. We've got x to some power. So we go x to the what power? Well, the first derivative, it's -2. Second derivative, -3. Third derivative, -4. So notice all of them are negative. And they're always one more than the derivative. See, this is the fourth derivative. I've got -5. So how do I say that? I'm just going to go n plus 1. So it's negative of the n plus 1. So now if I look at my first derivative, n is 1. So I have 1 plus 1, but it's negative. Then third derivative would be, the second derivative would be 2 plus 1, which is 3, -3. Then the third derivative, 3 plus 1 is 4, -4. Now let's see what the book came up with. Okay, what they did then was they said, okay, we're going to make the negative exponent just a positive exponent on the bottom. So that means what they did was -1 to the n factorial over x to the n plus 1. So whether you have x to the n plus 1 or on the bottom, or x to the negative n plus 1 on the top, it works out either way. So I kind of like mine because it's all in one line, nice and neat and orderly. But either way will do it. So the challenge here is just looking at the patterns and examining it as a sequence. And so we look for the sign first, then the coefficient second, and then the x value third. And notice whenever we want alternating signs, it's always going to be -1 to the n. Now, if I wanted the first term to be positive, though, then I would go -1 to the n minus 1, or n plus 1. So let's just say n plus 1. Now that means when n is 1, I've got -1 to the second, which is positive. So this will give you a positive, then a negative, then a positive, then a negative. Whereas the -1 to the n will give you the negative first, then a positive, then a negative, then a positive. So the change of sign is always going to be -1 to some power, and then notice the coefficients are just n factorial. Okay, piece o' cake. Let them eat cake. All right, cruising onward. Now we've got x to the fourth plus y to the fourth equals 16, and we want the second derivative. Okay, so that means we need to do this implicitly. Okay, that's it. Shut up. Yes, we're doing this implicitly. So, all we do is take the derivative of the first function. So, derivative of x to the fourth is 4x cubed. Now remember, I don't need a chain rule here because the x is a variable, not a function. But when I go to y to the fourth, that's going to become 4y cubed times the derivative of the inside, which is y prime, because it is a function. So we have the chain rule. Okay, equals. The derivative of 16 is 0. All right, now, I'm looking for the second derivative. I only have some function with the first derivative in it. I better get y prime by itself, and then I can take that derivative, and then it'll be happy. Okay, so we're going to toss our 4x cubed over the other side. So we've got 4y cubed y prime equals negative 4x cubed. And now we divide through by 4y cubed, so y prime equals negative 4x cubed over 4y cubed. So that means y prime equals negative x cubed over y cubed. Now, we need one more derivative. Now, there's a couple of ways we could do this. And in this case, since y to the fourth equals 16 minus x to the fourth, we could actually solve for y and plug it in. Or what we could do is take the derivative of the entire thing here and then substitute y prime when we get the y prime here. So let's do it that way. So what we do is we go y double prime equals. Okay, now we're taking the derivative of this whole thing. It's a fraction. So we better use the quotient rule. Okay, so we've got low, d high, so the derivative of the top is negative 3x squared, minus high, which is negative x cubed, d low, which is 3y squared. And we've got the chain rule. So 3y squared y prime over y to the sixth. So let's go over that. It's low d high minus high d low with the chain rule, square the bottom, and away we go. Okay, so let's clean this up. So we've got y double prime equals negative 3x squared y cubed. Now minus a negative is going to end up being plus the 3y squared, or let's keep the x's in there. X comes first in the alphabet, so we'll keep that in here. So minus 3x cubed, rats. 3x cubed y squared y prime all over y to the sixth. Now, 3, yeah, that's right. Okay, the last thing we need to do is plug in our y prime for what we know y prime is, because we can't have y double prime as a function of y prime. We need to get everything in terms of x and y. So what we're going to do then is substitute the y prime in here. So y double prime is going to equal negative 3x squared y cubed plus 3x cubed y squared times y prime, which is negative x cubed over y cubed, all divided by y to the sixth. Okay, so now we just clean this up, and notice I've got, well, okay, let's just go back over here, and y double prime equals negative 3x squared y cubed now, when I multiply all this junk, I'm going to have a minus in there, so it's going to be minus, now what do we have? 3. What happens to the x's? X cubed times x cubed is x to the sixth. Then what happens to the y? Well, y squared over y cubed makes divided by y to the first. And then we divide the whole thing by y to the sixth. Okay, now this is going to be easier to break this up into two separate chunks now. So we'll say y double prime equals, take the first chunk, negative 3x squared y cubed over y to the sixth is going to be negative 3x squared over y cubed, and then minus 3x to the sixth over, now this is going to be, if I flip the bottom and multiply, then I have 1 over y to the sixth multiplied here. So this becomes y to the first times y to the sixth is y to the seventh. So, yeah, we could get common denominators if we want to. Let's see what the book did. Okay, the book. Yeah, they did that. They got common denominators, and then, all right, we'll clean this up a little bit more. So let's just make some room up here. We're just doing algebra here. So y double prime equals all that junk. Okay, so first thing, we need common denominators, so we multiply this by y to the fourth over y to the fourth. So we've got y double prime equals negative 3x squared y to the fourth over y to the seventh minus 3x to the sixth. Okay, so next, we just factor out a y squared here. I mean x squared here. Let's factor out a negative x squared. So we have negative x squared times 3y to the fourth. Oh, rats. Let's factor out a negative 3x squared. Okay, it will be that way. So we have a negative 3x squared times the quantity y to the fourth plus x to the fourth, all over y to the seventh. Now, remember the original function was x squared plus y, or x to the fourth plus y to the fourth equals 16. Well, that means y to the fourth plus x to the fourth also equals 16. So now we can just plug in a 16 there, so we have negative 3x squared times 16 all over y to the seventh. So our final answer, y double prime, is going to be negative 48x squared over y to the seventh. So that is your simplest form. Now, a lot of times you're not going to be able to get a simpler form, but this one happened to work out nice and neat, so we could do that. So there's your final answer. That's it. Another piece of cake. All right. Now, let's go one last example, and that is